Well, hello, welcome again to Math 315. This is the second video in Chapter 7, and in this section we're just going to have a look briefly at Maxima and Minima, and then we're going to introduce a thing called Rolle's theorem. Now, you'll know most of this from high school. This is just doing again fairly formally something that you know from school. We're just doing it perhaps more elaborately and more technically. So we've got a function f, which is defined on some open interval, and we're going to say that f's got a local maximum. So we're thinking of a picture like this. We say it's got a local maximum at some number xi. Now, this is a Greek letter, the letter xi, sometimes pronounced xi or xi, and it's traditional to use this symbol here. If you don't like the xi, just write a C there, it'll do. But I'm just doing it because it's the traditional symbol that's used in this context. So we've got a local maximum at xi, and what that means is that there's some interval, you can draw a little interval, some interval around this point xi, and if you take any x in the interval, then f of x is less or equal to f of xi. And that means all these heights are going to be less or equal to this height, and you can see that's going to mean we've got a local maximum there. And we do a similar thing for local minimum. In this case, again, we say it's got a local minimum at xi, means there is some interval you can draw around this point, and if you take any x value in there, then the fx value will always be bigger than the f value at xi. And we call that a local minimum. So this one here will be a local min. Now, the result that you had at school, you've probably been using since high school, and that is if you've got a function which is differentiable, then if it's got a local max or minimum at c, then the derivative of f at c is 0. At school, you use it the other way round. To find the local max and min, as we'll do shortly, you take the derivative and put it equal to 0. This theorem is saying if there's a maximum or a minimum at that point, then the derivative is 0 there, which again is geometrically fairly obvious. If you draw a tangent line across here, it's going to have 0 gradient, and if you draw a tangent line across here, it'll have 0 gradient. Now, just a little proof of this result, which is not too hard to see. I'm going to do it just for the local minimum at c, so we're looking at this picture here now. Now, if we look at f of x minus f of c, so if I claim that there's a local minimum here at c, then f of x minus f of c is going to be a positive number, or possibly 0 if these are equal. So that means if I take this, which is positive or possibly 0, and I divide it by x minus c, where I'm now taking my x to be bigger than c, then if x is bigger than c, the bottom is going to be positive. So if I take a limit as x goes to c from above, I've got positive over positive is positive, and so this limit, whatever it is, it must be bigger or equal to 0. On the other hand, if I take the limit from the other side, if I go x goes to c from below, that means x is less than c, and that means this number on the bottom is going to now be negative. The number on the top is still positive. The number on the bottom now is negative, so this quotient will be less or equal to 0, and that means when I take a limit as x goes to c from below, whatever this limit is, it's less or equal to 0. So that means we can write this down here. We can say that the limit as x goes to c from below is less or equal to 0, and the limit as x goes to c from above of this is bigger or equal to 0. Now, the function's differentiable by assumption, and that means when I take either of these limits, they equal each other. So this is going to 0 and this is going to 0. And hence, by the pinching theorem, or some version of it, we have that the limit as x goes to c actually has to equal 0. It's squeezed between being less or equal to 0 and bigger or equal to 0, so it's got to be 0. But of course this limit is just our derivative formula, our derivative limit, and so the derivative is 0. Now exactly the same argument works for local maximum. Now in practice you should be able to find some local max and min, much the same as you did back at school. So we're going to, just as example here, find the local maxima and minima. In fact, they're going to be singular. It's really the local, I should really say perhaps local maximum, because there's only one, and minimum of the function, because there's only one of this function, x cubed minus 3x plus 1. So here's the worked solution, much the same as you would do at school. There's the function. To get the stationary points, we take the derivative, so I differentiate this, bring the power down the front, decrease by 1, and that differentiates to this, and I put it equal to 0 for a stationary point. Now, by the way, it's very important that you write these words for a stationary point. If I don't write that in, then this statement is not true. This derivative doesn't equal 0. It equals lots of different values. It doesn't equal 0. It only equals 0 at a stationary point. So as always in mathematics, what you write down has to make sense. You can't just put it equal to 0. You have to say 0 for a stationary point for the correct setting out. Well, it's easy to solve this. You put this on the other side, divide by 3. You get x squared is 1. So x is plus or minus 1. Now, we're not going to develop the second derivative test here. I'm just going to use our basic idea that you look at the gradient at each of these points. You look at the gradient each side of the stationary point. So this means I'm looking at the gradient a little bit less than 1, when x is a little bit less than 1, when x is a little bit more than 1. At 1, we know the gradient is 0. So we go back to the gradient up here. If I put a number a little bit less than 1, try 0 for example, then you'll get a negative number. If you put a number a little bit bigger than 1, try 2 if you like, plug that in, you get a positive number. So near this point, in some neighbourhood of this point, the gradients are going negative, 0, positive. And so we conclude that we have a local minimum at x is 1. A local min at x is 1. Now we do the same at x equals minus 1. So we make up our table. We're looking at minus 1. We know the gradient 0. We look at a number a little bit less than minus 1. So we're looking at minus 1 from below. And a number a bit bigger than 1. So we're looking at minus 1 from above. So put in a number that's a little bit less than minus 1. So again, put in, say, minus 2, if you like, back up into the derivative. And then when you work that out, you get a positive number. Take a number a bit bigger than minus 1, say 0, and you get a negative number. So the gradients this time are going positive, 0, negative. And that tells me then we have a local max at x is 1. And the conclusion then is f has a local minimum of minus 1. So if I put x as 1 back up into the original function, I get the value, I put minus 1 back up in the original, I get a value of 1. And if I put if I put minus 1 back up into the original one, I get the value 3. So in fact, this has a local minimum of minus 1 at x is 1. And a local max of 3 at x is minus 1. So the picture's looking something like this. It's going down, it's got a minimum here of minus 1 at 1. And it's got a maximum local maximum of 3 at x equals minus 1. And that's the picture there. The next example says to find the global max and min for this function x cubed minus 3x squared plus 1, but this time we're on the interval between 0 and 4. Because, by the way, this doesn't have, if I didn't have that there, this function has no global max, because this can, as x becomes very big, this becomes very big, and it's got no global min, because if x becomes very big negative, this is becoming very big negative, So there's no global max or min, but if I restrict the domain, then there will have a global max and min. Now to find that, what we need to check is, we need to find the local max and min in this interval, and we need to check the endpoints to find which is the biggest and which is the smallest. So here's the worked solution for this one. So here's my function f of x is x cubed minus 3x squared plus 1 on this interval. So once again we take the derivative, we get 3x squared minus 6x. We put it equal to 0 for our stationary point. So that SP there stands for stationary point, a point where the derivative is 0. Now out of this I can factor 3x out and I get x minus 2. And this is equal to 0, and that means then x is 0 from here or x is 2 from here. And again we make up our little table, so we look at the values, so at x is 0, we look at numbers a little bit less than 0, a little bit more than 0, and we're putting them back up into here basically. So if I put a number a little bit less than 0, so you put say minus 1 in, then you'll get a negative here, you'll get a negative there, the product's positive. It's 0 at 0. You put a number that's a bit bigger than 1 in, sorry, a bit bigger than 0, so put say 1 in. You've got to be careful you don't go too far away, so because of this here, put a number just a little bit bigger than 0, put 1 in, so you'll get you'll get positive and negative, so overall negative. So locally, near 0, the gradients are going positive, 0, negative, and that tells me I have a local max at 0. The at x is 2, a little bit less than 2, a little bit bigger than 2. A little bit less than 2, put 1 in, you'll get negative. At 2 it's 0, put a number a bit bigger than 2 in, you'll get positive. So this is going negative 0, positive, so I have a local min at x is 0. Now finally I have to check the values of the function. So I put 0 back into the original function, I get 1. I put 2 in, that's one of our that's the other stationary point, the one that we saw was a local min. You plug that in, you get minus 3. And I've got to check the endpoints. Now the endpoints were 0, I've already done that one, and 4. So when x is 4, you plug it back in, you get 17 for the f value. So that tells me f has a global maximum of 17. That's the biggest it can be on the interval when x is 4. So the maximum happened at an endpoint, but the minimum has a global minimum of minus 3. That happened at x equals 2. And that was at a stationary point. So the graph of this looks something like this. So there's 0 and there's 4. So at 0 we saw that this was up here. Where was it? It was at 1. So this function comes down. At 2, it takes the value minus 3, so it's coming down here like this, takes the value minus 3, and then at 4, it's going to have to cut somewhere here. At 4, it was all the way up to 17, so it's going to zip up here, so at 4, it's going to be up at 17. So this cubic is doing something like this, but we're only on the interval between 0 and 4. So there's your there's your global minimum, and there's the global maximum. One of them turned out to be at the end point of the interval, and one of them turned out to be at one of the stationary points. So this is what you do generally if you've got a closed interval. You have to check what the function values are at each of the stationary points, each of the local max and mins. See what the function value is at the endpoints. You take the biggest and the smallest of those. Now, derivatives can be used to show that certain equations only have one real solution. We've seen already how we could use the intermediate value theorem to show that a particular equation had at least one real solution. Now we can use them to show that they've only got one real solution, either on the whole real line or on some interval. So in particular, if a differentiable function changes sign between a and b, well, if it's differentiable, it's continuous. So if it changes sign by the intermediate value theorem, it must have a zero somewhere in between. And if the derivative is not zero in this interval, then f has exactly one real zero. If f is not zero, that means the function's either increasing, so it can't turn back on itself and cut the axis again, or it's decreasing. So we just have to check the derivative is not zero. So here's an example of this. We're going to show the equation x cubed plus 4x minus 1 has exactly one real root. And here is the solution here to this. There's our equation. And I look at this and I'm just going to try and guess some numbers to put in, so I can see that if I put in x as 0, then I'm going to get minus 1, which is negative. And if I put in 1, what happens if you put in 1? Well, you get 4, which is positive. So I just got these by trial and error. I just looked at it and thought, well, I'll try 0. I get negative 1. Put in 1, you get 4. So f is continuous. So we know by the intermediate value theorem f has a 0 somewhere between 0 and 1. We get the derivative of this function now, differentiate this, x cubed differentiates to 3x squared, 4x to 4, and this thing, whatever it is not 0, in fact it's positive, the function's increasing. It's not 0 for any x. So we know this function is always increasing, we know it's got one 0 between 0 and 1. And by what we said before, hence the f has exactly one real 0, and that means the equation x cubed plus 4x minus 1 equals 0 has exactly one real root. And the picture's looking something like this. So there's going to be functions increasing. There's only going to be one real root to this function. Well, we'll see some more of these in the tutorial problems. Finally, we're going to get to the mean value theorem in the next recording, but in this subsection we're going to introduce, firstly, Rolle's theorem is a special case of the more general mean value theorem, and I want to do that in this recording. And we'll do an example here, and then we're going to use Rolle's theorem to get to the mean value theorem, but in the next recording. So Rolle's theorem is a funny thing. It's, again, you look at the geometry firstly of this. So what it says is you've got a function f, here it is, that's continuous and differentiable. And all it says is, and it's on some interval a, b, it just says that if f of a and f of b are equal to each other, if these have the same height, then there must be at least one stationary point between the two. There's got to be at least one number psi so that f dashed of psi is 0, that is a stationary point. Geometrically it's fairly obvious. I'll just state it carefully here. So here are the conditions. F is defined and continuous on the interval AB with a less than b, and it's differentiable on the open interval. And we're going to suppose that f of a equals f of b. Then the theorem says there is at least one, there may be lots of them, but there's at least one point psi somewhere in here so that the derivative of psi is 0. Now, since Rolle's theorem is just a stepping stone to the more important mean value theorem, I'm not going to go through the proof of it here. So I'm not going to go through the proof of this here, but we will do one quick example just illustrating Rolle's theorem. And so the question says, illustrate Rolle's theorem for the function x cubed plus 2x squared minus 3x on this interval. And so here is the working out for this one. So here is our function x cubed plus 2x squared minus 3x, and we're on the interval 0, 1. So to check Rolle's theorem, I've got to check what happens at the two endpoints. So if I put x as 0 in, you get 0 plus 0 minus 0 is 0. You put x as 1 in, you get 1 plus 2 is 3 minus 3 is 0. So the values of the two endpoints are the same. F of 1 equals f of 0. So Rolle's theorem says there's got to be a psi somewhere in between so that the derivative is 0 at that point. Now, we're going to find explicitly what this number is. Again, if you don't like psi, just put a c here or something. We're going to find explicitly what this is. So I'm going to take the derivative of this function. We get this quadratic. And this is going to be 0 at x equals this number psi. Well, I can solve this using the quadratic formula. It doesn't factor nicely, so use this using the quadratic formula. So I get minus b plus or minus square root of b squared minus 4ac on 2a, which comes out to be this. After you simplify it, you can take a 4 out of the sum of these two. I think this is 52, which is 4 times 13, so you can simplify it and get this. Now we're only taking the positive root because we're in the interval between 0 and 1. So if I took the negative root, I'd be outside the interval. And this number on your calculator is about 0.535, and so my psi is the number minus 2 plus root 13 on 3. So there's the psi. It's not halfway, but it's roughly 3. So there's the psi where the gradient is 0. So that's just an illustration of Rolle's theorem. In the next video, we will use this to develop the mean value theorem.